Good morning, everyone. So today we're going to our next topic in our mechanics chapter, and that's forces. So what consists of a force? Well, usually we think of forces as pushes and pulls, but actually forces, they will go well beyond this simple explanation. Actually, they can change the motion of a body. So forces, basically, well, it's something that can change the motion of something, or it can deform the shape of bodies. They can act on a distance, or they can act in contact. So sometimes we have forces like electromagnetic forces, which act on a distance, gravitational forces, they act on a distance, and we also have contact forces, which, well, we have to, like when you push something or pull something with your hands, you are in contact with the object. Now, we should remember from our first chapter that forces, they are vectors, so they should have some kind of magnitude and direction. Usually what we do is what we call a free body diagram. So for example, let's say that we have a situation in which I have some kind of a block that's really common, right? So this is the floor, this is our block, and I'm exerting some kind of force here. And that's how we represent it. This is a drawing, right? This is not a diagram. This is the free body diagram. We assume that the force is acting on the center of mass of that object. So we can just represent as a vector force to the right. In this case, we would have some other forces. So there is one force which is gravity, and the force, because of gravity, we call that force weight. This force here is someone pulling, right, this block, and we would also have a normal force. Since this block is not going through the floor has to stop this block from going under, right? So those would be the forces, and this is our free body diagram. So free body diagram. Sometimes in the first item of forces or IB question, you're going to just draw the free body diagram. So what you have to do is find all the forces which are acting on your object and express them as vectors, and all of them should be applied to the center of mass of your object. Now, a very important topic in forces is our Newton's laws, and they are going to give us the tools that we need to not only understand the problems but also to be able to predict things. So our first Newton law, so we've got Newton's laws of motion, alright? So the first Newton law of motion is inertia. Inertia is basically our tendency to keep moving if we're moving, or to keep still if we're not moving, unless there is some force acting on us. So for example, here in this block that we have in the previous example, there is some force acting on it. So it would not be moving at a constant speed because there is a force, right? There is a resulting force here. Those forces, the gravity and normal force, they would cancel out because the block's not moving up or down, but horizontally it would accelerate to the right. So what does inertia tells us? Well, if you're still, you will remain still, and if you're moving at constant speed, you will still move at constant speed unless there is some force acting on you. This is noticeable, for example, when you're in a bus or in a car, and for example the car stops suddenly, or the vehicle stops suddenly, basically your tendency is to keep moving forwards. You feel like the urge to keep moving forwards. There might be even an accident. Can you imagine? For example, sometimes the car crashes and the person just goes flying off the window, right, the front window, and that's because of inertia. The person was moving, let's say the car was moving with the people at 100 kilometers per hour. So when the car stops, the person will keep moving, right, unless something will stop it, like the window or the floor or another car in front of them. So that's inertia. That's the first law. Now what if I don't have a situation in which all the forces are canceling out, so I'm not in a situation where I'm inert, so I'm not moving at a constant speed. So then we have the second law. So the second law, Newton's second law, tells us that if there is a force acting on our object, it will accelerate our object depending on how massive it is. If it's more massive, it will accelerate less. If it's more massive, it will accelerate more. From this equation, in fact, you could express mass in a kind of different way now. Take a look at this. So mass could be understood now as the ratio at which the speed of some object changes when you apply some force. So if a body is very massive, you will need to apply a lot of force for its speed to change the same amount. Is it clear? A few things to take note here is that, well, mass is a scalar. That's fair enough, right? You don't. What's your mass? You're gonna say, okay, 70 kilograms. You don't have to say upwards, down, to the left or right. But acceleration is a vector. So our force will be a vector, and it's going to be in the same direction as our acceleration. So, for example, in this first example that we had here, this block, same block again. All right, and I've got this force to the right. So the forces up and down, they are canceling out. So my free body diagram is simply an arrow to the right. And if you were told that the mass of this object is 1 kilogram and this force is 10 newtons, we could find out the acceleration, right? So we know that force is mass times acceleration. So we can rearrange. Acceleration would be our subject, so we would have force divided by mass. Now our force is 10 newtons, that's SI unit, and our mass 1 kilogram. So in this case, our acceleration would be 10 meters per second squared. All the units are in SI units, so I can just keep meters per second squared here, because the result will also be in the SI unit. Now please notice that those units, we could write them in a different way. I think this was done a few times in our first chapter. But let's take a look. Newtons, right, per kilogram, and meters per second squared. So we could also understand that the unit for newtons is actually the same thing as kilograms meters per second squared. We should know that by now, right? Those are the same unit, they are equivalent. However, SI unit is newtons. Fair enough. Now we also have our third law of motion. And the third law of motion tells us about action and reaction. So basically it states that for every action, there will be an equal and opposite reaction. So this will create our action and reaction pairs. Okay, so for example, if I'm moving a box, so I'm applying some force. If I am the one pushing that block, I will feel a force as the block is trying to be prevented from moving. So there will be a pair of action and reaction. So, alright, this is like the person pushing the block forward. Right, I am making this force forwards, the box will feel a force going to the left here, but the block will also exert a force to the right, trying to oppose the movement that I'm trying to make it have. Okay, so let's take a look at an example now. So a car with a mass of 1,500 kilograms accelerates uniformly from rest to a speed of 28 meters per second. So about 100 kilometers per hour. So we're given the conversion here. In a time of 11 seconds, calculate the average force that acts on the car to produce this acceleration. So, well, we know the mass of the car. Oops, that's our mass. This is uniformly from rest, so it starts at 0, and then our final velocity or speed, right? Because we don't care about the direction here. In the time of 11 seconds. So from these, we can find our acceleration. This acceleration should be the change in velocity, so final velocity minus initial velocity divided by time. So what's our final velocity? 28. Initial velocity was 0, time 11 seconds. And this makes sense. You've accelerated to 28 meters per second in 11 seconds, right? So that's 28 divided by 11, that would be around 2.54 meters per second. Okay? It's hard to see here. So 2.54 meters per second. There you go. Okay, so that's our meter per second squared. That's our acceleration. Well done. So we know the mass, we know the acceleration, so force, our Newton's second law, mass times acceleration. So the mass of the car is 1,500 kilograms, and the acceleration of the car is 2.54 meters per second squared. So if we multiply those two numbers, we should get 3.8 kilonewtons, right? This is obviously two significant figures, okay? Because I only know two significant figures of this one. I know 3 of this one, so this is the one I know the least. So I'm going to keep the result to two significant figures. Now, 3.8 kilonewtons is the same thing as 3,800 newtons. So those would be acceptable answers. And now, what is producing that force? Well, it's actually the motor, right? The motor in the car will spin, and it will try to spin the wheels. So basically what's happening here is that you've got the wheel, which is being turned by the motor, right? There's a complex system, but we can simplify it as just the wheel being turned by the motor. And then as the wheel is turning, it's trying to move the floor backwards. But the floor doesn't move. So as it's trying to move the floor backwards, the floor moves the car forwards. So that's why the car moves forward. And what is actually producing that force is the motor, which is trying to spin the wheels. Alright, so another example here, very simple one. An aircraft of mass 3.3 times 10 to the power 5 kilograms takes off from rest in a distance of 1.7 kilometers. The maximum thrust of the engines is 830 kilonewtons. Calculate the takeoff speed. So now we know the mass, we know the distance, we know the force, and we want to find out the takeoff speed. So we can find the acceleration, which is given, the acceleration of the aircraft. You would basically divide, right, 8.3, which is your force, by your mass. This is F equals ma. This wasn't supposed to be here. Now F equals ma. So F equals ma. Now I know the mass and I know the force. So if I rearrange this, I would have acceleration would be force divided by mass. Now force 830. 1,000, right? Kilo, that's 1,000, so times 10 to the power 3. Divided by, now my mass 3.3 times 10 to the power 5. Right? So if you divide those two, then you get this result, which is the acceleration. Okay, this shouldn't be here. That would be the first thing that it would calculate. Now we know the acceleration now, right? And we want to find the final speed. So the aircraft takes off from rest, right? So if it takes off from rest, we know that our initial speed is 0. And now that we know our acceleration, we can find our final speed. We know the distance, right? So which equation, which CVAT equations should we use? Now, to answer that question, you have to remember that we have one equation that does not have time. It's not dependent on time. And that's probably the one that we're going to use, right? Well, so our CVAT equations, we have an equation that will give us the final velocity squared will be the initial velocity squared plus 2 times the acceleration times the displacement. Now, the initial velocity is 0, so we only need those values, right? And we know the final, we know the acceleration, we know the displacement, so we can just multiply 2 times the acceleration that we have found, 2.51. This is meters per second squared, this is kilometers, so we would have to convert 1.7 kilometers to meters. So let's put all the units. Meters per second squared times 1,700 meters. So when we have both here in meters, we will have our speed in meters per second, right? So v squared would be then 2 times 2.51 times, well, let's just calculate the final speed then. So if we multiply those and then we get the root, we would have the velocity, final speed to be 92.4 meters per second. Now, very importantly, this is the speed because it's not a vector, it's a scalar. However, if we were told the direction of the force, this speed would be the magnitude of the velocity vector, which would also be in the same direction. And the acceleration would also be in the same direction. So all vectors here, force, velocity, and acceleration, they would point towards the same direction. So here, we were told that this force is to the right, or north, or whatever, then all of those vectors, they would also be pointing towards the same direction. So, I'd like to show you now a few examples of free body diagrams. So, because there will be some situations which we're going to see many times. So it's important for us to take a look at a few examples so we know how to work with them later. So let's say that the first case is when we have simply a ball falling, or whatever object, right, falling under gravity with no air resistance. So it's just free fall. We've covered that, right? So a ball falling, this is the pull of the earth on the ball, and the earth is actually, right, there's a pull of the ball on earth. It's just that this is too small because the mass of the ball is negligible compared to the mass of the earth. Now if you draw your free body diagrams, the acceleration of the ball is downwards, right, and basically the ball's being pulled down. So it would just be a point, which is your ball, it represents your ball or your object, and an arrow downwards representing the pull. If you had more than one force, remember that those forces, they should be in scale. So that would mean that the vectors, they would have to be up to scale. So if a force is twice as strong as another one, then the vector has to be twice the length. Alright, so very simple situation here. We've got a ball or any other object which is just standing on the ground. So here's our object. No acceleration, so no force. Well, the free body diagram for this one, we're going to have the weight of the ball, which is pulling downwards. So there's a force because of the Earth, this ball is an Earth, so it's feeling the effects of the mass of the Earth, so there will be a force down. However, since it's not going inside of the Earth, there will be some resistance from this surface to prevent this ball from going inside. So this would be our free body diagram. We've got the ball, which is our point here in the middle, then force on the ball from the ground, that's the ground which is stopping the ball from going inside, so there'll be a force upwards, and a force downwards, which is the force of the Earth. The Earth is pulling the ball down, so that's the weight. Now let's say that we have a slightly more complicated case here. So we are inside an elevator, and this elevator is accelerating upwards. Alright? So if we were to analyze the motion of this object, we would have to draw a free body diagram first. But we could actually draw two different free body diagrams. So we could have a free body diagram just for the object, which is inside of the elevator, and a free body diagram for the actual elevator. So let's first look at this object. So there will be a force downwards, which is weight. However, the elevator is going upwards. So I would have a force upwards, which is my normal force. It's preventing the object from just going through the elevator downwards. But I also have, since this is accelerating upwards, I will also have another force up, which is, well, the force to accelerate this object upwards with the elevator. So if we draw a free body diagram, we're going to have a force down, which is the force exerted by the Earth on the object, which is our weight. And we would have a force up, which is the force exerted by the lift on the object. Because here both those forces, they will be the same force. The only difference is that this normal force, it will not be that small anymore. It will be a bit larger, because now the elevator is having to produce a stronger force. It's going to resist more. If this floor was too weak, it could break when this elevator goes upwards, because it's having to resist a force which is larger. Anyway, so this is the normal force. This is the force that the elevator will have to, so the lift will have to act on the object, so it doesn't go through the elevator. So that's why we have those. It's important to notice that this vector is larger. It means that this force is larger than this one, so it's up to scale. If we observe the lift, however, we'll see that, well, there's a force downwards here because the ball is there, so it's trying to prevent this elevator from going upwards, right? Inertia. Also, the Earth is pulling the lift down, so there is the weight of the lift itself. The lift is being held by a cable, it's being pulled by a cable, being pulled upwards, so there will be a force here, and the acceleration of the lift is also upwards. Alright, so let's take a look at the situation here, and let's solve it ourselves. So let's say that this is not being accelerated, it's all still, right? Nothing's moving here, so all forces, they should be in balance, right? By the principle of inertia, which is Newton's first law, if nothing is, well, the speed here is zero, right? Everything's speed is zero, so nothing's moving. So by inertia, I would have, well, this would still be the same situation. And by Newton's second law, I would have that the resulting force would be zero, because F equals ma. If there is no acceleration, there will be no resulting force. So all the forces here, they are canceling each other out. So let's draw the free body diagram. Okay, I'll just write FBD, free body diagram. So this is our middle point here. This is a ring, could be a joint, could be a knot between those ropes, it doesn't matter. Now, we're going to have a force downwards because of this weight. So I'll just describe by W, which, if we were to measure it, if I know the mass of this object, m, and the acceleration of gravity, g, okay, this is our acceleration of gravity, we would have simply mg. this would be our force downwards, which is the weight. Now we have a string to the left, so there will be some force to the left, which we can just denote by a vector going to the left, and that's what we call tension. So we could label this as tension 1, since we're going to have another string going elsewhere. Right, so we could also describe this force, and we know that this angle here is theta, and that's another tension. Right, that's a string here connected to the spring, but it's a rope, isn't it? It's important to notice, I know this sounds obvious, but it has to be said at some point. Tensions, they can only be a pull. You cannot have a push, right? So it's always pulling. You cannot push a rope. I mean, well, it wouldn't exert a force, so it has to be stretched, right? Now, if you remember what we have done before with vectors, we could decompose those vectors. In fact, since this is not moving, by Newton's second law, the sum of the forces, by inertia, Newton's first law, the sum of the forces would be 0. And by Newton's second law, we can decompose this into the forces on x will be 0, and the forces on y will also be equal to 0, because there is no movement on x nor y. So if the sum of the forces on x is 0, let's decompose this vector t2. So we still have the same t1 to the left. We have our weight down. We have a horizontal component of this tension T2, and we have a vertical component of tension T2. Now if you notice in your booklet, this horizontal one, if you're trying to get the horizontal component here, it would be T2 cosine of theta. And the vertical one here would be T2 sine of theta. Take a look in your booklet, your physics data booklet, that should be there. So you have those values now, and well, since those are cancelling out, weight and T2 sine of theta will have to be the same, and T1, T2 cosine of theta will also have to be the same. So since those are cancelling out and those are cancelling out, the sum of forces on x is 0, so I will know that the magnitude of T1 will have to be T2 cosine of theta. Same thing for the y-axis, for the vertical forces. I would have that the weight, which is mg, if I know the mass of my object, right, it would be T2, so mg, it has to be equal to T2 sine of theta. If this was moving in any direction, then you would have some force being added here, and this wouldn't be equal to 0. And now let's quickly talk about friction, solid friction. So let's say that I'm trying to move. Alright, so let's say that we have an object on a surface, and I want to move that object with a force. Well, you've probably noticed in real life, if you try to move something, if you apply a very, very small force, that object will not move. Well, that's because of friction. So when we're trying to move two solids against each other, if we could look at this in a microscopic scale, this is not flat, right? Everything that we have here, which looks flat to us, so this is like zooming in. If you could zoom in a very small portion here, you would see that it's actually all rugged, all uneven, and when you try to move those things around, they will try to stop each other, right? It's just like, well, that's friction. That's the definition of friction, right? So what happens here is that it's going to be hard for you to move those things, and there will be a minimum force that you have to apply for the object to start moving. So this first kind of force that we discuss, which is the minimum amount of force for you to start moving an object, is what we refer to our static friction. So that's the force to overcome the static friction. So basically, static friction is the one that happens, is the kind of friction that happens, that occur when you don't have any movement between surfaces, any relative movement. So why do I say relative movement? Well, they could both be moving at the same speed, but then there would be no relative movement. So, well, there wouldn't be any force between them. Well, there could be, but the point is that it wouldn't be. It would be static friction because there's no relative movement between each other. For example, if you're in a car and the car's moving, you're moving with the car. It's a static friction because there's no relative movement between the two things. And you also have dynamic friction, which is when there is already some kind of relative movement between your two objects, your two solids. Dynamic friction happens when you have first when you overcame your static friction, so the objects are moving, and then if you realize in real life, it's hard for you to start moving something, but as soon as it starts moving, it's easier for you to keep moving it, right? So in this case, when it's already moving, right, you already have some kind of force, some kind of velocity, and this is not moving, so there will be dynamic friction, and this value is usually much smaller than this one, because the static friction is a large value for you to start movement, and then when it's already moving, you get to dynamic friction, which you can lower, for example, the speed, or you can even decrease the force and still have some movement. So mathematically, we can describe those two kinds of friction. So let's discuss static friction first. So static is quite simple. When you're trying to move the object, the two surfaces, they will resist the force. So I'm applying, let's say, force here to the left, and there will be some reaction, which I'm going to call our static force. This is our static force, our static friction force, right? So this force, which is trying to overcome, it's trying to prevent the movement, it will always be less or equal to a coefficient which we call the static coefficient and our normal force. I'm calling it R here. So there will be a weight down, which is because of the earth, and there will be a normal force upwards. So we use the same value of the normal force and we multiply by this coefficient. So what happens here? Let's assume that you are trying to move that block and you start with a force of 0. So this is a graph of your force. So as you increase your force, the block will not move. And when you reach a certain force, which is, so let's say that this is mu s r. This is our static friction. When you reach this value, when you cross this value, then the movement starts. Movement starts. Alright, when you cross through this value, when your force is larger than this value, if you produce any force which is lower than that, your static friction will be exactly equal to that force. So it will be exactly how much you would need to overcome it. So if you produce, let's say, this amount of force, only this, your static friction will be exactly what is needed to prevent that movement. When you cross above this point, then you will have to change to your dynamic friction, because now there's movement. So dynamic friction is, well, basically trying to stop your object from moving. And the equation is not that different at all. We denote our friction by a different, and now it's equal to a coefficient coefficient of dynamic friction times your normal force. So this is the force that will always be there when you're moving an object and there's friction. And notice that this is equal to, because now that you have movement, this will always be the same. If you decrease, for example, you've reached your dynamic friction. If you start to decrease the force, the object will only stop now when you reach this new force. And that's basically it. Those coefficients, they are a property of the material pair, so it depends on both surfaces. So if you have wood and wood, you would have a certain value. If you have rubber and metal, you would have a different value. If you have let's say your shoes and ice, you could find out well, if you could slip or not on the streets if you go out on a snowy day. So let's quickly take a look at this example. So a box is pushed across a level floor at a constant speed with a force of 280 newtons at 45 degrees to the floor. The mass of the box is 50 kilograms. So first calculate the vertical component of the force, the weight of the box, the horizontal component of the force, and the coefficient of dynamic friction between the floor and the box on the floor. So let's do it. So we're trying to decompose this force. This is the horizontal angle. If you look at your booklet, you would have, well, this is the force, right, going on that direction. That's exactly the force that the box is gonna feel because of the source, right? So we would also have the weight of our box going down, and this is 45 degrees, and there you go. And we have also the reaction of the floor, which is trying to prevent this block from going inside of it. So if we're looking for the vertical component, so letter A, that's simply, well, our initial force, right? The vertical component of this force. So vertical is sin, so 280 times sin 45. So that would be our force of 198 newtons. Letter B, the weight of the box. That's mass times gravity. So the mass of the box is 50 kilograms. So that would be 490 newtons. 9.8 here, 490. Letter C, the horizontal component of the force. Now instead of using sine, now we're going to use cosine. So 280 cosine of 45, and that would be 198. Well, sine of 45 and cosine of 45, they are the same. And well, this force is exactly in the middle, right? So it's going to be shared equally horizontally and vertically. Now D, the coefficient of dynamic friction between the box and the floor. So we know that there is a constant speed. So if there's a constant speed, I know that the sum of the forces is 0. So if the sum of the forces is 0, I can work out some of those relations here, right? Because the force, which is forwards, it will not be enough to make the oh no, it's only dynamic. So the sum of the forces is 0. If we look for our vertical forces here, so this reaction force, since the box is not going inside the floor, I will have the weight and the vertical component of forces, right? So this will have to be equal to this weight plus the vertical component of this force. So I will actually have to add those two forces. So my reaction force is 688 newtons, right, pointing upwards. And my coefficient of dynamic friction would be simply the ratio, right? I would have our force divided by our friction force divided by our resistance. Now this friction force, since the box is moving at a constant speed, this force forwards is this one.